Welcome to lesson 4.10. Today we're going to look at balancing oxidation reduction equations. Hopefully you've looked over lesson 4.9 and understand how to assign oxidation states. And I briefly mentioned in that lesson that when we can add electrons to balance charge on both sides, those are the easiest types of oxidation reduction half reactions. So we'll look today at the more difficult types. So a half reaction is just simply where you split the chemical reaction into the half that involves oxidation and the other half that involves reduction. So what we'll have to do on this, you'll have to not only balance the number of atoms, types of atoms and number of atoms, but you also have to balance the charges as well. So we'll start off just like we did before in that brief little introduction in the last lesson. We'll write separate equations for the oxidation reduction half reactions. For each half reaction, the first thing you'll do is you'll balance all the elements except for hydrogen and oxygen. When you balance oxygen, you have to do that using water. And to balance hydrogen, you do that using protons or hydrogen ions. And you do have to do that in that order. Balance the oxygen first, then the hydrogen, and then when you're done with that, you'll balance the charge using electrons. Sometimes we have to, because the number of electrons lost equals the number of electrons gained, sometimes we have to take one or both balanced half reactions by an integer to equalize the number of electrons. When you add the half reactions together, you're going to cancel identical species just like you would if you were adding equations in math. And then you're going to go back and check that the elements and charges are balanced. And so here is a schematic of putting together the balancing the equations for the oxidation reduction reactions. So just a couple of examples as we go through these slides, and I will use the slides here instead of drawing on them as I did on the last lesson, because I think these slides are very well put together. Not that I didn't think the last ones were, but potassium dichromate is bright orange. It can be reduced to blue-violet when it becomes chromium ions. So under certain conditions, potassium dichromate reacts with ethanol as follows. And notice it says now to balance the equation using the half reaction method. So the compound or the element that is reduced is the chromium, and we do have to leave it in its compound as we write reactants and products on that. Notice we have oxygens on the left-hand side, the reactant side, that we don't have on the product side. The other equation is the ethanol being reduced to carbon dioxide. Notice that we have hydrogens on the left-hand side that we don't have on the right-hand side. So first off, we're going to use water to balance out those 7 oxygens. So the 7 oxygens on the notice, I'm sorry, I skipped a step. First notice that we balanced the chromium. So we had 2 chromiums on the left, 2 chromiums on the right. Now we're going to balance the oxygens by adding 7 waters over here. So we're going to add 7 waters on this side. What that does is that it adds additional hydrogens, and so what we have to do is we have to go back. So it's going back and forth and back and forth. We have to go back and we have to put 14 hydrogens on that side, and that's going to balance out that equation in terms of the elements on both sides. But if you'll notice, on this side we have 14 positive charges and a negative 2, so we have a total of a plus 12 charge over here. And on this side, we have a total of a plus 6 charge. Sorry, not writing very well right now. And so we will have to go and we will have to add some electrons to make both sides equal plus 6. Now we're going to look at the oxidation half reaction. First off, we want to balance the element that is not oxygen or hydrogen, so that's carbon. So we're going to put a 2 in front of that carbon dioxide, which is going to cause us to have 4 oxygens. So instead of messing with the ethanol, we are going to add 3 waters. So now we have 1 plus 3 more. So we have 4 oxygens on that side. That causes us to have to use hydrogen on the product side because we have 5 plus 1, so 6 hydrogens there, plus 6 more is 12, and so we're going to put 12 over there. You'll notice the left-hand side of the reaction has a total charge of 0, and the right-hand side has a plus 12. And so we're going to have to add 12 electrons to this side to get it to equal 0. Now, when we add in the reduction half reaction, we had 6 electrons. We added 12 in the other one. So we have to multiply the whole reduction half reaction by 2 to make sure we have the number of electrons lost equals the number of electron gained. So here are the two half reactions with everything balanced. And so we have 12 electrons on both sides. That's a good thing. We have 28 hydrogens on this side and 12 on this side, so that 12 is going to cancel out. We're going to end up with 16 over here. Dichromate we're leaving alone. Chromium we're leaving alone. We have 3 waters on the reactant side and 14 on the other side, so we're going to change that to 11. And everything else should be balanced. So when we put that together, we're going to end up with 16 hydrogens, 2 chromate ions. Then we're going to move down to the second line. We have the ethanol and then nothing else, arrow, 4 chromium ions, 11 waters, and the only thing left down here is those 2 carbon dioxides. So that's how you balance that. And most people think that's a lot of steps, but it is what gets you to your solution. So when we go back and count on the reactant side, we have 22 hydrogens, 4 chromiums, 15 oxygens, 2 carbons, and then on the product side, the same. And then when we balance it out, we have a plus 12 charge on the reactant side and a plus 12 charge on the product side. Sometimes when we do these reactions, they're either occurring in an acidic or a basic solution. So for example, this last one we just did, is occurring in an acidic solution because we have access to protons. But if it occurs in a basic solution, you're not going to have access to protons, and so you have to do an additional step once you've got it balanced. And so in that additional step, what you're going to do is you're going to add enough hydroxide ions to both sides to turn all the protons into water. We'll go ahead and skip that critical thinking. So silver is sometimes found in nature as large nuggets. More often it's found mixed with other metals and their ores. An aqueous solution containing cyanide ion is often used to extract the silver using the following reaction that occurs in basic solution. So we're going to balance the oxidation half reaction. We have silver, which is starting out as a 0 going to a plus 1. The cyanide doesn't change charge, but it is involved in this particular reaction because it does combine with the silver. And so we have to balance the carbon and nitrogen. And we're going to do that simply by putting a 2 in front of that. So now we have a minus 2 charge on the reactant side and a minus 1 on the other side. So we're going to add 1 electron to the product side. So that is our oxidation half reaction. Reduction half reaction, what we have is oxygen. And so oxygen, we're going to balance that with water, just like in what we did previously. We're going to balance that with water. Now we have to go back and we have to put 4 protons or 4 hydrogen ions. And then we have to balance the charge. So the product side charge was 0. The reactant side, since we put those 4 hydrogens, we had to put 4 electrons. We have to multiply the oxidation reduction by 4, since we only had 1 electron there and we had 4 in the other one. Add the half reactions and cancel the species. So there's our 2 half reactions. Cyanide is good, the silver is good. The electrons cancel out because we have 4 electrons on the reactant side, 4 on the product side. And then we have we have protons and we have water that we're going to leave in there. Now remember, this occurred in a basic solution, so we don't actually have access to this. And so what we're going to do is, because we have 4 protons, we're going to add 4 hydroxides, but we need to do that to both sides. So it's just like in math, we need to add those to both sides. And that will make us have, let's back up a little bit. Because that makes 4 waters on this side and 2 on this side, that's why it balances out to 2 here at the end. So you have to eliminate as many water molecules as possible. Check that the elements and charges are balanced. The same thing before. Do an atom inventory. That looks good. Do a charge balance. That looks good. And then we'll finish up this particular lesson with just talking about oxidation reduction titration. So we can use this process and do analytical methods with it. Some of the common oxidizing agents we use are potassium permanganate, potassium dichromate, and cerium hydrogen sulfate. Personally, I've never seen cerium hydrogen sulfate, but potassium dichromate and potassium permanganate are very colorful, and if we reduce them, then we're going to change their colors. So when we have permanganate, it's purple, and then the manganese plus 2 ion is almost colorless. It kind of turns a blackish brown. And so then we know when we've reached the end point of a titration. In this particular example, your end point, you would just see, you'd start out colorless, and then when you added just an extra tiny little bit of potassium permanganate, says it's purple, then you would see a light purple color in your solution. Okay, so that concludes lesson 4.10. We're going to, before we take the next exam, we're going to look at a chapter on gases.